So this task was using the criteria D, the applying maths in a real life context. So you have these like paper cups and you're told the measurements. So of cup A, so A is this first one here. This one has a lip piece of 1.3 centimeters and the whole cup is 9. So we could quickly find out that the main part of the cup here is 7.7 centimeters. Okay, that's just from doing the 9 minus 1.3. And we now know what the main body of the cup is. And then we have a second cup, which is cup B. And we don't have much information about this. We just know that a stack of 4 is 14.7 and a stack of 8 is 19.3. Now the first question is that we're making a single tower of cups and we want to compare how many of cup A and how many of cup P and their respective heights of the towers. And we want to know which tower is going to be the tallest. So one thing that you can do here is, since we've got 4 in stack of cups for B, we could see how much 4 in a stack of cups for A might be as well. So we can compare a stack of 4. So stack of 4, and we know that cup B is equal to 14.7. We can see that straight away. Cup A, now cup A, you're going to have the main base of it, which is 7.7. We calculated that already. And we're going to need to add on to that an additional, 4, since we're doing a stack of 4, of the lip size, which is 1.3. So 4 lots of 1.3. And that will then tell me how big a stack of 4 cups in cup A will be. So we can put that into our calculator and we find that it's 12.9. And therefore cup B is the taller cup. So cup B is taller. Okay, and then we could actually do that again, but this time instead of a stack of 4, maybe we could do that with a stack of 8. Okay, since we've also got a stack of 8 there for cup B. So we know that cup B is equal to 19.3. And again, I'm making sure to always use my units. This is criteria D. And now I'm going to compare that with cup A. And again, I'm going to have that 7.7 for the base. And then I'm going to have 8 lots this time of the lip size, which is 1.3. So I'm going to again type it into my calculator. So this is just 7.7 plus 8 times 1.3. And this time I have a stack size of 18.1 centimeters. And again, cup B is taller. However, when we look at those two numbers, when we only had a stack of 4, cup B was quite a lot taller, almost 2 centimeters taller. Whereas with this stack of 8, it's only just over a centimeter taller. So you can see that the difference there is changing. So will it always produce a taller tower? Probably not. The lip size might be different compared to the base size, and we need to start and investigate that a little bit further. We can't just assume that B is always going to be taller. So one way we can do this is to think about the equation that models this pattern. So for cup A, it's a little bit easier to see because we have, you can see from what we've already done here with the two calculations, both here and here, that we have this base amount and then however many I'm looking for, lots of the lip. And that's the same thing each time. So the equation is that the height is equal to, and then I have this 7.7 plus, and then it's 1.3, which is the lip size, lots of x, where x is the number of cups. So again, I should make sure that I just explain there what my x or h might be. So h is the height and x is the number of cups used. So that forms a linear equation, and I could think of that as h is equal to 1.3x plus 7.7. So it's exactly the same. I've just written it the other way around so that it is in the form y equals mx plus c that I'm used to seeing. So I'm going to try and come up with an equation in the same way for cup B. Now cup B, so far all I know is the total height of a stack of 4 and the total height of a stack of 8. So I'm going to subtract those two together, and if I subtract 19.3 from 14.7, then I find that the difference here is 4.6. So I have a 4.6 centimetre difference. Now, given that this is the same in both, and this one I have 4 of the lip, and this one I have 4 of the lip here, the only difference is the fact that on this second stack, I've got an additional 4 lips. So that must be equal to this difference in my number. So that means that to find the height of each lip, I'm doing 4.6 divided by 4, and that gives me 1.15. So I now know that each individual lip is 1.15 centimetres. So using that, I can now try to find how big the main stack is at the bottom, okay? So the base of the stack. So the first one tells me that I've got a stack of 4 equaling 14.7. So I've got 4 times 1.15. Now that is equal to 4.6. So if I subtract the 4.6 from the 14.7, then that tells me how big the base of the cup is. So 14.7 minus 4.6, and that gives me 10.1. So I now know that the base is 10.1, which means that the equation of cup B is going to be the height is equal to 1.15 for the lip plus 10.1. So I now have an equation for both cup A and for cup B. And I can now use this to help me to work out if they will always be the same or if they might be different. So I want to know at what point might they be the same height, because we know that they're going to be different. We know that they're going to intersect because the gradient is different. So if I think about the graph here, so I've got x, the number of cups, and the height of each stack, then the first one is a gradient of 1.3 and it goes through 7.7. So we go through 7.7, and I'm just roughly sketching this, and it's a gradient of 1.3. And this is roughly what cup A looks like. And then cup B goes through 10.1, so it goes through a little bit taller. That's the y-intercept. But it's got a gradient of 1.15, so the gradient is actually gentler. So it might be something like this. So at some point, you're going to get this intersection. And to start with, cup B is going to be the taller one, okay, which is what we found. A stack of 4 and a stack of 8 must be in this region. But at some point, we're then going to find that A is actually the taller stack and that B is smaller, because the lip is smaller, so what you're adding on each time becomes less and less. So the best way to find that intersection is to find when the two equations are equal to each other. So to do this, we're going to have cup A, which is 1.3x plus 7.7, And we've got cup B, which is 1.15x plus 10.1. And we're going to try and find when are they equal to one another. So 1.3x plus 7.7 is equal to 1.15x plus 10.1. So to start off with, we're going to take off the smallest value of x. So I'm going to subtract here 1.15x from both sides. So I've now got 1.3 minus 1.15, which is going to be 0.15. X plus 7.7 is equal to 10.1. So now I'm going to subtract 7.7 from both sides of my equation. And 0.15x is then equal to 10.1 minus 7.7, so 2.4. And then I'm going to divide by 0.15. So I'm dividing by 0.15. 2.4 divided by 0.15 is equal to 16. So at the point 16, so where x is 16, where I have 16 cups, then they are equal. So if I was to stack 16 cups together, they will be equal. Anything less than that, cup B will be taller. Anything more than that, cup A will be taller. And I can then write that down and use that as an explanation. So a stack smaller than 16 will lead to cup B being taller. A stack larger or bigger than 16 will lead to cup A being the larger stack. So you can then explain that in a lot of detail there. Now, section 2, or question 2, says that we're now trying to fit how many of each of the cups can go into this height of 210. So now that we've got the equations, it's going to make it a lot easier. So we can kind of think of this question in two halves. The first one being for cup A and the second one being for cup B. So for cup A, we know that the equation is that the height of the stack is equal to 1.3x plus 7.7. So we want to know how many can I fit into 210. So this is what I'm trying to work out. So I'm going to first of all subtract 7.7 from both sides. And that gives me 202.3, which is equal to 1.3x. And now I can divide by 1.3. And I now have that x is equal to 155.615, and so on. So that means that the most cups I can fit in is 155. I can't round up like I normally would to 156 because it's just not going to fit. Instead, I have 155 cups and I have a little bit left over. Okay, so it's 155 cups that would fit in for cup A. And then for cup B, I'm going to do the same thing again, but this time with the equation for B. So I know that the height is equal to 1.15x plus 10.1. And I'm trying to think how many are going to fit into 210. Now I'm expecting this to be more because we know that cup B is a smaller stack. So I would expect more cups to fit in. So 210 is equal to 1.15x plus 10.1. I'm going to subtract 10.1 from both sides. That then gives me 199.9, which is equal to my 1.15x. And then if I divide through by my 1.15. That then tells me how many cups I can fit in. And approximately that is 173.826. So that means that I can fit in 173 cups of size B. Okay. Now again, we want to think about our real life application. So we're thinking about our rounding. Okay, and we've explained that there. We would need to write that down in words on the exam paper as well. But we're thinking about the fact that we can't have part of a cup, and so we're going to have a little bit spare space, but we need to round it to the nearest whole number. And you're also going to think about any real life implications. So for example, if the cups don't stack exactly, or if one of them isn't quite fitting in properly, then that could impact the final result. Also, maybe when you stack that many cups together, if you've tried to stack that many paper cups, they probably have a little bit of a wobble on them. They might be going diagonal. It might be quite hard to keep them entirely vertical, and therefore perhaps you can't quite fit that many in, because if it's not exactly straight up, if for example they're fitting at a little bit of an angle here, then you might not fit quite as many, or you might fit more because it might have like a little bit of a wobble in it. Okay, so you can talk about those impacts from real life as well. And then we have question 3. So question 3 is then asking you to think about how we can fit the most number of cars in the boot of this car. Okay, now this is a view from above. So we need to lie them flat in one continuous tower. Okay, a single linear, so straight line tower. So this is actually similar dimensions to the door previously. So one thing I could do is just create my stack of cups along here. Okay, so that's my original and then all of my stacks. And I can try and work out how many will fit. And we already know the answer to that, as we did it previously. So we can just, well, we don't even need to use cup A. We know that cup B is going to fit more. So we know that that's going to give me 173 cups. However, there might be a way to fit more in as well. Okay, so instead of stacking them up in this same way, instead, to get the most number, the longest straight line we can fit on that rectangle will be a diagonal straight line. So we want to work out how long is it going to be diagonally, and then we can work out how many cups will fit into it. So to do that, we need to use Pythagoras to think about the length of that diagonal. So we know that the Pythagoras theorem is a squared plus b squared equals to c squared, where I have 210, and these can be in either order, it doesn't matter, plus 90 squared is equal to c squared, which is my diagonal. Okay, so I need to try and work out how long that diagonal is. So 210 squared is 44,100, and 90 squared is equal to 8,100. So when I add those two together, I get 52,200. And then I need to square root that. And that means that I've got 228.47 for my diagonal. So it's 228 let's round it to 5, and I can talk about the rounding that I've done, that I'm trying to fit it into. So I can answer these really similar to question A, and I can just set my equation equal to 228. Okay, so to do that, I would have my equation for B, which was equal to 1.15x plus 10.1. Okay, I don't need to do it for cup A because I know by now it's going to be a smaller number. and I can have 228.47 equal to that 1.15x plus 10.1. So I'm going to need to subtract 10.1 from both sides. So this is very similar to the previous question. So 228.47 minus 10.1, and that's 218.37. And then I'm going to divide by 1.15. So I now have 218.37 divided by 1.15, and that gives me 189 point, and I'm going to round this to 89. So that would give me 189 cups. However, I now need to think about this in terms of real life. So if I have 189 cups, that's assuming that my cups are essentially going to be stacked like this in a straight line. But if you imagine kind of zooming in here on this corner, the problem is, if I kind of zoom in a little bit, I have my corner and the cups can't fit exactly to the end, because when I place that first cup and then the second cup and the third cup and so on, there's going to be this little bit of extra space that I can't quite use, okay, because they're not going to quite go into that corner. So to get the maximum marks here, you needed to think about this and then try to find a way to work out a rough approximation, because we can't do it exactly, of how much space we might be missing. So you're told that the base of the cup, so the bottom, if I think about the base being here, and then the top of the cup being this end, you're told that the base of the cup has a measurement of 4.5. So this is 4.5 centimeters across the base. In which case, we've kind of got a little triangle there where we have 4.5 and we've got a value here and here. Okay, so using Pythagoras again, because it's a right angle triangle, I can say that something squared plus the same thing squared is equal to 4.5 squared. So I'm going to think of it in terms of x. Okay, so in terms of x there. So 2 lots of x squared are equal to 4.5 squared. And 4.5 squared is equal to 20.25. So 2x squared is equal to this, which means that if I divide by 2, I find that x squared is equal to 10.125. And then when I square root my answer, I find that I've got x is around about 3.2. And I'm having to be approximate here, okay? So roughly I'm missing 3.2 on each side. And now I can try to work out how much this lost distance is. So if I know that this is 3.2, and I know that this side here is also 3.2, I can work out a smaller triangle. So this part here, where this is 3.2, this we know is right angled. We can see here that's right angled. And it's going to be half of the 4.5 and therefore 2.25. So again, I can use Pythagoras. So this time I have 2.25 squared plus something squared, let's call it x again, is equal to my longer side of 3.2 squared. So 2.25 squared is equal to 5.0625. and 3.2 squared is equal to 10.24. So I'm going to subtract the 5.06 from each side. And that gives me x squared is 5.1775, in which case, when I square root that, x is equal to 2.75. So I now know that I'm wasting 2.75 roughly in terms of the amount of space missing. And I could do the same for the top end, and then I can work out what is my new distance that I'm able to use, okay, which will be a little bit less than 2.28. And I can again repeat this same step and work out roughly how many cups I might be able to fit in. And there's lots of different answers here, depending how approximate you want to be, how you've placed them, and so on. Because all of this is an estimation, because this is not going to be exactly the same 3.2, 3.2, because it's not a square, it's a rectangle. And we can't therefore be entirely precise, okay? But we can do our best and talk about the approximations that we've made and talk about what it is that we've done. And you're going to get something around 1.84 cups, okay, to be your final answer. It could be around there, and so long as you've justified why, then that would be fine. So the better answer is to go from that 189 and get it reduced down by considering the fact that it can't go exactly to the end points of that diagonal. So that last question in part 3 has a lot of potential to be able to use the criteria D to talk about your rounding, your estimating, and really to think about how you've answered the question in the context of the real world.